everyone. It's great to be at the summit, to see friends and meet a lot of people working on work that has a lot of impact in the area. So today, I was going to talk about autonomous capabilities we have on our rovers on Mars, and particularly in the context of the Perseverance rover and the Ingenuity helicopter, which is what I work on right now. And I'm going to focus on the self-driving capability, but also talk about beyond that, the capabilities that we are working on these missions. So AI is really making it possible for NASA to do missions that we couldn't do before. And this is an example that I'm going to give. The slides moving? Oh, there we go. So Perseverance is part of a much larger mission called the Mars Sample Return Mission. And the goal of the Mars Sample Return Mission is to bring back samples. One sec, let me just fix this. I think I'm moving too fast. There we go. It's slower than I expected. I'm going to keep talking to it. But the Perseverance is part of a much larger mission to bring back samples from Mars, and it's the first step of the mission. And the goal of the mission is Perseverance is going to collect sample cores from the surface of Mars, and then there's going to be a subsequent mission with a lander that's going to land with a robotic arm that will transfer the samples from Perseverance to the lander, and it is going to put them into a canister. And for the first time, we'll have a rocket that'll launch from Mars. And this is a joint NASA and ESA mission. And there's a ESA orbiter that's going to be on Mars orbit, with which we're going to rendezvous and transfer robotically the canister and then bring it back to Earth, which will be the first time we ever bring back samples from Mars to Earth. So when we were looking at this mission and said, we want to bring back samples from Mars, we wanted to go to the place where it would be the most interesting samples. If you're going to bring them back for the first time, you want to bring the most interesting samples. And the place the scientists chose was Jezero Crater. And on the back, you are seeing that delta in the crater. So it's a crater with a delta where there's a river channel that flowed in. And so if you're going to find signs of life, the most likely place is a place that has water. But the crater walls are tens of meters, so it wasn't going to be possible to land there safely without potentially landing on a big cliff. So what made this possible was autonomous capability, where we have the spacecraft, as it's entering the Mars atmosphere, it's taking images and comparing them to a pre-built map. And it's trying to do this registration in real time during the time, and it needs to do it really fast because there's only 7 minutes we have from the time we enter the Mars atmosphere to the point we land. And this is showing an example in this video of the images that were taken, and it's doing landmark detection, and it was able to find a solution in that period of time. And you'll see the green are the features that it's detecting, and the rest are the outliers. And it converged on a solution and found that we were headed right for a crater, and ended up doing a divert maneuver to divert us to a safer spot on the other side of this hazard zone. So we were diverted from the crater, but now, instead of being closer to the delta, we were all the way on the other side. And so in order to get to the delta, we were going to have to do this really long drive all the way across. But we'd anticipated this possibility. And so we had self-driving capability on the rover. And initially, after we landed in the south, we took the opportunity to explore a really interesting region in the crater floor called the South Setar region, and then decided we were going to have to drive to the delta. That's about a 5-kilometer drive all the way around. And the white path is showing the path of the rover. And the white dots, those are the places at which we stopped. And we wanted to move. The self-driving capability, what it lets us do is go very fast between regions that are interesting. On prior missions, this would have taken us a year to do. And with Perseverance's self-driving capability, we were able to do it in a month, which is completely unprecedented for planetary exploration. And it really, this particular capability, as we were doing this exploration, we realized we were really trusting the AI more and more because it was performing so well. And I'm going to show an example. The inset there shows a region where we had multiple sols. It was a long weekend. And we let the self-driving capability drive on its own continuously for 3 days on Mars. And it did a region of driving all the way around the southern tip and covered this terrain and very successfully ended up getting us to the next destination. And in this slide, you're seeing the area where on the ground we do planning. On the left is actually, so this was a drive on Sol 350. The actual visualization we use augmented reality to sort of look at the terrain, but we also have people suggest to the AI what the best path might be. But it knows better once it's on Mars, and so it ended up picking the path. On the right, you're seeing the actual path that we took. And this is a picture of what the terrain looks like as it's driving. So this is from Mars on Sol 351 at the middle of that drive. And this video is video from the hazard cameras taken by the cameras that actually take the images that are used by the onboard navigation. So these are the images in which it's looking for hazards and navigating around the terrain. And at the end of the drive on the right I'm showing, it also has to figure out if you can still talk to Earth. Because if you can't talk to Earth, that's pretty much the end of the mission, because it might be going, but we would never know. And Earth can be really low in the sky, and so the rover's body itself can occlude the view to Earth. And so at the end of the drive, it'll autonomously try to find a communication to Earth, and if it can't, it'll drive some more till it finds a spot in which it can actually do the turn. And so we now have this capability where we are driving really, really far, much further than we could before. But that means that we can cover a lot of distance, and as we are driving those distances, we may miss out on things. We may miss out on really interesting features that are along the way. So we didn't want to do that, and beyond self-driving, I'm going to give a couple of examples of some of the capabilities we worked on. And so this is Autonomous Exploration for Gathering Increased Science, AEGIS, where we take a wide-angle image as you're driving. So look at a whole swath of terrain, and then on board, the AI will look at it and figure out, is there something interesting here? Mostly, if you shot in the blind with a narrow field of view imager, you'd hit dirt. But this is an image from Sol 462 on the mission, where AEGIS found this really interesting rock. And once it finds the rock, it shoots a laser at it, so you can see the red crosshairs where it shot the laser and then took a telescopic image. That's just 2 centimeters across. So you're looking at a terrain meters away, a whole wide scene, and shooting these really small targets. So now we've gotten to the point where we're trusting the AI not just to drive the rover, but shoot lasers. And we're pretty comfortable doing it because it's been so successful. And it knows that even if there's a fault on the rover and the arm got left out, it's not going to shoot the arm and is capable of detecting that. One of the really interesting areas of work for the autonomous capabilities is actually the robotic arm. Because when we get really close to the surface, we can see things that we just can't from orbit. And the rock, even what we see, is exposed to a lot of weathering. So we cut away these circles, 5 centimeters in diameter, to clear off the top of the surface and then place instruments on it. So you're seeing an example of this 2-meter arm with a 45-kilogram turret sort of positioned on it. And then we also collect intact rock cores from the surface. But there's a huge opportunity for onboard capabilities here because we do a ton of simulations, we do a ton of testing, but we are going to a place where no human has ever gone before. So there's a lot of things that it behaves differently than what we might expect. So our problems are always plagued with very low sample training data we have, and then we also have very imprecise models. And this is an example just a couple of weeks ago where we were at the Novorupta abrasion spot, and we abraded the surface, and the terrain around it completely changed. And then we drilled and cored a rock core, and that further changed the topography. And now we are placing instruments with all the tailings and the changes, and you need to get within a couple of centimeters and make sure that the lens on the arm or the cameras don't get corrupted by this terrain, or you don't ram it into a feature. In spite of all that, we've now collected 14 rock cores, and this shows the cross-section, the side view picture taken by Perseverance of the rock cores that we've collected so far. And as you can see, because we've been able to drive to such different regions, there's a wide diversity of samples. And it's actually really exciting. And the scientists are so excited that we've got like a really good sample set that we're actually getting ready to cache it. So the red star shows the location that the rover is at right now. And then in the middle of that image is the Three Forks region, where very soon we will take all these tubes and we'll drop them on the surface so that when we do the Mars sample return mission, there are actually backup helicopters. Because Ingenuity has been so successful, these are helicopters with wheels and robotic arm that can actually pick up these samples and bring them back to the lander. So talking about the helicopter, one of the other things we had on this mission was a helicopter. Because we can access the surface, but there's so much more we can do if we can fly on Mars. But we didn't actually know if it was going to be possible to fly on Mars. We've done tests in Earth environments, but the atmosphere on Mars is 1% the atmosphere on Earth. So flying on Mars is like flying at 100,000 feet on Earth, and no rotorcraft on Earth has ever done that. But we had Ingenuity as the test vehicle that we were using, and was strapped under Perseverance and flew to Mars. And this was another example where Ingenuity was being powered by the rover while it was attached to it. But once we deployed it, it was going to need to charge its solar panel. Otherwise, it wasn't going to survive the night. And we can't, Mars is so far away. So if you wait for an entire sol, that was going to be too long. So this had to be autonomous, where we would deploy the helicopter, had to be pretty sure that it was actually released and not dangling off, and then drive away. And that drive really had to succeed, because otherwise the rover would still be on top of Ingenuity, and it wouldn't have survived. This was before the first flight. Well, that worked out pretty well, and we were able to demonstrate that you can fly on Mars. And this is a video of the third flight where Ingenuity is going to take off. It goes to about 5 meters above the surface, and then it flies about horizontally about 50 meters. It's going to go, this image, this video, is being taken by Perseverance. It's going to fly out of the field of view of the camera, and then it's going to come back. It has a camera for navigation that's looking downward, and it takes images and is able to autonomously navigate, because obviously, the time delays wouldn't allow us to fly it from Earth. And this has been so successful that we now have completed 33 flights on Mars with Ingenuity. And one of the things with the rate at which we're making progress with AI, just in general as a field, is that you really have to reevaluate the plans we had for what we were going to do and try to consciously add these capabilities in it. Because without it, we might actually not make progress in these missions at the rate at which we could. So one of the other things I was going to bring up here is, as we are driving, we use these augmented reality capabilities ourselves. So when you look at the terrain with, we use 3D goggles, it really is like being there, and you're looking out at this amazing Martian vista, and it's sort of very immersive. At the same time, that capability right now, we don't have a way to share. We do put all the images that we take on Mars on our public websites, but it's harder to do that. We're also building missions, robotic missions. We have prototypes, balloons to go to Venus, and snake robots to go down the vents of Enceladus, and aerial robots for Titan. And looking at the future, having AR, VR capabilities that are going to allow people to participate in this and see sort of the exploration from their own perspective and be part of these missions, and also beyond that to future missions and places that we might go to. So that is some of the ongoing work for the future, is how do you, include and make everyone part of this exploration. And with that, I'm going to end with some of these links which allow you to get some more information, and I'd be happy to answer any questions that come up.
Vandy, thank you very much for that, and beautifully illustrated as well. We would like to ask the audience whether you'd like to ask any questions before we let you leave the stage. Have we got any questions for Vandy? Raise your hand, please. Yes, gentlemen here, if we could get a microphone over. Here is one coming now.
Well, thank you for your presentation. It was amazing. I was watching the TV when I saw you talking about the Ingenuity helicopter that they flew first time, so I want to congratulate you for that achievement. It's amazing. My question will be, you are using AI to solve some problems on some space missions. My question will be, do you plan to use AI to actually plan a mission to tell you what could be a future mission that could be interesting, that maybe for humans we don't pay attention to that?
Yeah, that's a really good question. We're using AI to be like, solve this specific problem that I put before you, but could you open-endedly say, what's the best mission design or what best missions to do? There are actually people looking at that. So we do have people who are working on using autonomous capabilities, because there's so many possibilities. And in fact, you can do it both at the level of where we should go, what missions we should optimize, but also the specific design of the robots. Like, what robot should we design? Should it have wheels? Should it fly? So yeah, that's a very interesting area of work. That would be really cool. I'm excited for a mission where it's like an AI decided this was the mission we should do to search for life.
Thank you. Do we have another question for Vandy in the audience? Please raise your hands nice and high so we can see them. I think do I see one over there? Ah, here we go. This lady on the end, please. About 4 rows back on the right. Here we go. Microphone just coming to you.
Thank you. Awesome talk. I was wondering, do you know if the samples that you have found, what's the percentage of the similarity of samples that you find on Earth? Do you know this yet?
What's the percentage of the samples?
Like, similarity,
Right, that's a great question. So what's so interesting is we do have instruments on the rover where we're cutting over the rocks and we study them in situ, because we want to know the context in which we collected these samples. But we are limited by what we can do on Mars. If we send these instruments, they have to be packaged into really compact sizes. But when we bring them back to Earth, we'll have laboratories all over the world. So we do know, and that's the information the scientists are going to use to pick which ones to bring back to Earth, because we're actually not going to be able to bring all of them back. And they're going to utilize that information. It's not perfect, but we definitely have that information.
I have a follow-up question. Do you have potentially like sequencing, like, are you able to do any kind of sequencing with the machinery that you have?
When you say sequencing, do you mean sequencing in order to, like, planning, tell the robot what to do?
No, DNA sequencing.
Ah, I see. We don't have that capability. So it is capable of, if we found organics, we have instruments on board that can tell us that we found organics, but we don't have the capability to do full DNA sequencing. Now, that would be another really cool instrument to have.
That, unfortunately, ends this session. Vandy Verma, it's been wonderful hearing from you. Thank you again for all your questions. I'm sure you can approach Andy in the break. Thank you.
Thank you.
Now, companies and entrepreneurs, like a lot of you, want to aim for moonshots, but how do you land those moonshots? That's going to be the question we're going to be